Right now, in your pocket, on your dashboard, humming along in the servers that run your bank, there is a signal so weak, so faint, that anyone with a few $100s of equipment could hijack it. It travels more than 20,000 kilometers from a satellite in orbit down through the atmosphere, and by the time it reaches your phone or your car or the control room of a power station, it is barely a whisper. That whisper is what keeps the modern world synchronized. It tells your bank exactly when a transaction happened. It tells an airplane exactly where it is. It tells a power grid how to stay balanced. And because it is so faint, it is astonishingly easy to drown out, or worse, to fake. In 2026, a team of scientists in Adelaide, Australia, working with the country's National Science Agency, built something that could finally close that gap. They did not build a bigger antenna or a stronger transmitter. They built a device that uses one of the strangest phenomena in all of physics, something Einstein himself once called spooky action at a distance, and turned it into a tool for protecting time itself. To understand why this matters, you have to understand just how much of daily life quietly depends on a handful of satellites most people never think about. These are the satellites that make up what is known as the Global Navigation Satellite System, or GNSS. The most familiar version of this system is GPS, the American constellation that most phones and cars use, but there are others too, operated by Europe, Russia, China, and beyond. Every one of these satellites carries an incredibly precise atomic clock, and every one of them is constantly broadcasting a timestamp down to Earth. Receivers on the ground use those timestamps to calculate not just location, but exact time, down to billionths of a second. This sounds like a small technical detail, but it is the invisible heartbeat of the modern world. Financial markets use satellite timing to timestamp trades to the microsecond so that transactions can be sequenced correctly and disputes can be resolved. Power grids use it to synchronize the flow of electricity across vast distances so that generators feeding into the same network stay perfectly in step. Telecommunications networks use it to keep cell towers talking to each other without garbling calls or dropping data. Container ports use it to track ships. Emergency services use it to coordinate response times. Aircraft use it for navigation, and increasingly, so do the growing fleets of autonomous vehicles and delivery drones now moving through our skies and streets. All of this rests on a signal broadcast from satellites hundreds or even tens of thousands of kilometers away, a signal that has to travel an enormous distance and arrive weak, fragile, and shockingly easy to interfere with. It is worth pausing on just how precise this timing actually needs to be. We are not talking about clocks that need to agree down to the second or even the millisecond. Many of the systems relying on GNSS timing need synchronization down to microseconds, or even nanoseconds, billionths of a second. That level of precision only became possible because the satellites themselves carry atomic clocks, devices that measure time based on the extraordinarily consistent vibrations of atoms, typically cesium or rubidium, which oscillate at such stable and predictable frequencies that they can serve as some of the most accurate timekeeping instruments ever built. An atomic clock in orbit can remain accurate to within a few nanoseconds over the course of a day, and that stability is what allows GNSS to broadcast timing information so precise that a receiver on the ground can use tiny differences in signal arrival time from multiple satellites to calculate not just what time it is, but exactly where it is standing, often to within a few meters. It is a genuinely elegant system, one of the great engineering achievements of the 20th century, and it quietly became the invisible clock that the entire world eventually agreed to set itself by, largely without most people ever realizing it had happened. That fragility is not a hidden flaw. It is baked into the physics. A satellite cannot broadcast a powerful signal down to Earth the way a local radio tower can, because the satellite is far away, power constrained, and broadcasting to an enormous footprint of the planet at once. So by the time the signal reaches a receiver on the ground, it is spread out and weakened dramatically. Engineers have known about this vulnerability for decades, and for just as long, so have people who want to exploit it. There are two main ways to attack a satellite navigation signal, and both are alarmingly accessible today. The first is jamming, which is exactly what it sounds like. A jammer simply floods the area with noise on the same frequency the satellite is using, overpowering the real signal so that receivers cannot pick it out. Jamming devices used to be expensive, specialized military hardware. Today, some can be built with parts ordered online for a few $100s, small enough to fit in a backpack or plug into a car's cigarette lighter. Truck drivers have used cheap jammers to avoid being tracked by their employers. Drone operators have used them to shield illegal flights from detection. And in conflict zones, jamming has become a routine tool of electronic warfare, used to blind an opponent's navigation systems, guided munitions, or communications. The second attack is more insidious. It is called spoofing, and it does not just block a signal, it replaces it. A spoofing device broadcasts a fake satellite signal that looks completely legitimate to a receiver, time-stamped and formatted exactly like the real thing, except the location or time information embedded inside it is false. Because the fake signal can be made stronger than the real one, a receiver can be tricked into locking onto it instead, accepting a manufactured position or time as if it were genuine. This has already caused real documented chaos. Ships navigating through contested waters have reported their GPS suddenly showing them located at an airport hundreds of kilometers away. Commercial aircraft flying near active conflict zones have reported navigation systems suddenly jumping to false positions mid-flight, forcing pilots to fall back on old-fashioned instruments and manual calculations. And because so much critical infrastructure quietly depends on the timing signal buried inside GPS, not just the location signal, spoofing does not only put vehicles at risk, it can desynchronize financial systems, confuse power grid controllers, and disrupt telecommunications networks that most people assume are far more resilient than they actually are. The frequency of these incidents has been climbing sharply in recent years, particularly in regions touched by conflict. Pilots flying through parts of Eastern Europe and the Middle East have increasingly reported sudden, unexplained jumps in their onboard navigation readouts, sometimes showing the aircraft hundreds of kilometers from its actual position, forcing crews to rely on ground-based radar guidance and old-fashioned dead reckoning until the signal clears. Maritime shipping has faced similar issues, with vessels near contested coastlines occasionally reporting GPS traces that place them squarely inside restricted airports or military installations, an unmistakable sign of deliberate spoofing rather than a simple technical glitch. Aviation and maritime safety organizations have started tracking these events specifically, cataloging them as a distinct and growing category of incident, separate from ordinary equipment failure, because the pattern makes clear that this is a deliberate and increasingly common tactic rather than a rare anomaly, and it is not confined to conflict zones. Criminal actors have used jamming to defeat vehicle tracking systems tied to stolen cargo, and researchers have demonstrated, in controlled tests, that spoofing attacks could in principle be used to manipulate the systems increasingly guiding autonomous vehicles and delivery drones, an unsettling preview of vulnerabilities that will only become more consequential as automation spreads further into daily life. For years, the response to this problem has mostly been defensive patchwork. Better filtering algorithms, backup systems using ground-based radio towers, more sensitive receivers designed to detect obviously anomalous signals. These help, but they do not solve the underlying issue, because the core vulnerability is a matter of basic physics. A radio signal, no matter how cleverly encoded, is still just a radio signal, and radio signals can always, in principle, be replicated, amplified, and faked by someone with the right equipment and enough determination. If you want a truly tamper-proof solution, you cannot just make the fake harder to produce. You need a signal that cannot be copied, even in theory. One where any attempt to intercept, measure, or replicate it inevitably changes it in a way that immediately reveals the intrusion. That is where quantum physics enters the story, and where the team at Australia's Commonwealth Scientific and Industrial Research Organisation, better known as CSIRO, built something genuinely new. The device at the center of this breakthrough is called the quantum light source, and it was developed by CSIRO researchers working alongside Australia's Defence Science and Technology Group in Adelaide, with early design collaboration from Heriot-Watt University in Scotland. What it produces, at its core, is a stream of entangled photons, individual particles of light linked together in a way that has no equivalent anywhere else in nature. To understand what makes entangled photons so powerful for this application, it helps to step back and think about entanglement itself. When two particles become quantum-entangled, their properties become correlated in a way that defies ordinary intuition. Measure one particle, and you instantly know something definite about its partner, no matter how far apart they are, whether that is a few meters, or, as in this case, hundreds of kilometers, with one photon sitting in a ground station on Earth, and the other traveling all the way up to an orbiting satellite. Einstein was famously uncomfortable with this idea, which is why he called it spooky action at a distance. But decades of rigorous experiments have confirmed again and again that entanglement is real, verifiable, and, as it turns out, extraordinarily useful. Here is the property that makes it so valuable for securing a signal. Quantum states are fragile in a very specific and very useful way. If anyone tries to intercept, measure, or copy an entangled photon without permission, the very act of measurement disturbs its quantum state. There is no way around this. It is not a limitation of current technology that better engineering might someday overcome. It is a fundamental law of quantum mechanics itself, one of the deepest and most well-established principles in modern physics. This means that if someone tries to intercept the entangled signal traveling between the ground station and the satellite, tries to copy it, redirect it, or spoof it, the interference leaves an unmistakable fingerprint. The quantum correlation between the two photons changes in a detectable way, and the system immediately knows something is wrong. Unlike a classical radio signal, which can be recorded, analyzed, and perfectly replicated by anyone with sufficiently sophisticated equipment, an entangled quantum signal cannot be copied without destroying the very thing that makes it useful. This is sometimes described as being fundamentally spoof-proof. Not just difficult to spoof, but mathematically, physically impossible to spoof without immediate detection. The engineering challenge here was not proving that entanglement works. Physicists have known about quantum entanglement and its security applications for a long time, and quantum key distribution experiments using entangled photons have been demonstrated in laboratories, and even over some real-world fiber optic links for years. The real challenge, and the genuine achievement of the CSIRO team, was taking something that normally only survives in a carefully controlled, vibration-free, temperature-stable laboratory environment, and compressing it down into a rugged, portable, field-deployable device that could actually be used in the real world, outdoors, in variable weather, connected to a real ground station, sending photons up to a real satellite hundreds of kilometers overhead. At the heart of each quantum light source is a surprisingly simple physical component, a small glass cube. Laser light is directed into this cube, and inside it, through a carefully engineered nonlinear optical process, pairs of photons emerge already entangled, traveling outward in two different directions. One of those photons is kept on the ground, held inside the optical ground station. Its entangled twin is sent up through an optical link toward an orbiting satellite payload. Despite the vast distance between them, hundreds of kilometers of empty space, the entanglement holds. The correlation between the two photons persists, and that persistence is what allows this system to function as a real-time integrity check on the entire timing link. CSIRO's technical lead on the project, Dr. Matt Broom, has described the work as a genuinely significant milestone in the development of quantum-secure time transfer, and it is worth sitting with what that phrase actually means. Time transfer is the process of synchronizing clocks across a distance, and secure time transfer means doing that in a way that cannot be silently corrupted by an adversary. The team behind this project reportedly joked that if they could not build an actual flux capacitor to travel through time the way fiction has imagined it, they could at least build something to protect it, a high flux entangled photon source instead. It is a small joke, but it captures something true about what they accomplished. They are not manipulating time in some exotic science fiction sense. They are protecting the integrity of the timing signals that our infrastructure depends on every single second of every single day, ensuring that when a clock says a certain moment has arrived, that information can be trusted completely. 2 of these field-ready quantum light source units have already been delivered to the Defense, Science, and Technology Group in Adelaide, marking the transition of this technology from laboratory prototype to a fielded capability. The primary motivation is defense-related, and that context matters. Modern militaries depended enormously on precise positioning, navigation, and timing, often abbreviated as PNT, for everything from coordinating troop movements to guiding precision munitions to synchronizing communications across dispersed units. In an era where electronic warfare has become a standard part of modern conflict, where jamming and spoofing are actively used as tools to blind an adversary's navigation and communication systems, having a timing source that is provably immune to tampering is not a luxury, it is a strategic necessity. If a system built on this quantum foundation detects tampering, it does not just flag an error and hope for the best. It can prompt an automatic switch to an alternate channel, maintaining continuity even while confirming that an attack is underway. That combination, detection plus resilience, is precisely what defense planners have been chasing for years, as GNSS jamming and spoofing incidents have grown more frequent and more sophisticated around the world. But the implications of this technology reach well beyond the battlefield, and this is where the story becomes relevant to almost everyone, even if they never think about satellite timing at all. Precise timing from GNSS underpins a staggering amount of civilian infrastructure that most people simply take for granted. Financial markets, as mentioned earlier, rely on synchronized timestamps to sequence trades correctly across exchanges that may be located on opposite sides of the world, and any disruption to that synchronization can create confusion, disputes, or worse, opportunities for manipulation. Telecommunications networks rely on precise timing to keep data flowing correctly between towers and switching stations, and a timing failure can ripple outward into dropped calls, corrupted data transmission, or network-wide instability. Power grids are perhaps the most consequential example of all. Modern electricity grids are enormously complex systems in which generators, substations, and transmission lines across huge geographic areas must remain synchronized in near real time to avoid instability that can, in worst-case scenarios, cascade into widespread blackouts. Transport systems, from rail networks to shipping to increasingly automated logistics chains, depend on synchronized timing to keep everything moving safely and efficiently. Emergency services rely on synchronized time to coordinate response across multiple agencies during a crisis, when seconds and accurate location data genuinely matter. if a technology like the quantum light source can eventually be adapted, scaled, and deployed more broadly across civilian ground stations. It opens the door to a future where these critical systems are no longer solely dependent on a signal that is inherently vulnerable by the nature of its physics. Instead, they could have access to a verification layer that is mathematically guaranteed to reveal tampering the instant it happens, rather than relying purely on detecting anomalies after the fact, or hoping that jamming and spoofing attempts are simply too unsophisticated to succeed. This does not mean every phone or every car is about to get a quantum entanglement receiver built in. The current systems are specialized, still relatively expensive, and require dedicated optical ground station infrastructure to function. But the same was once true of GPS itself, which began as an expensive, specialized military system before eventually becoming a ubiquitous civilian technology embedded in nearly every device we carry. The trajectory researchers are pointing toward is one where quantum-secured timing eventually filters down from strategic defense applications into critical civilian infrastructure, protecting the backbone systems that keep economies and societies functioning smoothly, well before it becomes something an ordinary consumer interacts with directly. It is also worth putting this achievement into a broader global context, because CSIRO is not the only organization racing to solve the vulnerabilities baked into satellite navigation and timing. Around the world, multiple nations and research institutions have recognized that GNSS dependence represents a significant strategic risk, and they are pursuing different technical approaches to reduce that risk. In the United Kingdom, a company called Inflection has developed and flight-tested a quantum navigation system known as QINS, backed by several £million in funding from UK research and innovation. Rather than using entangled photons, that system relies on ultra-cold atoms, a fundamentally different quantum approach that measures extremely subtle changes in atomic behavior to determine position and movement without needing to rely on external satellite signals at all. It represents an entirely different philosophy, essentially building a self-contained navigation system immune to jamming and spoofing because it does not depend on receiving any external signal in the first place, rather than securing the external signal itself. In the United States, government agencies have invested tens of millions of dollars across a range of programs aimed at building resilience into positioning, navigation, and timing infrastructure, including efforts to revive older ground-based radio navigation systems as a backup to satellite signals, and programs exploring the use of low Earth orbit satellite constellations as an alternative or supplement to traditional GNSS. These varied approaches, quantum entanglement for tamper detection, ultra-cold atom sensors for self-contained navigation, revived ground-based radio systems, and new satellite constellation architectures all reflect a shared recognition across multiple governments and research institutions that the world has become dangerously dependent on a handful of fragile signals, and that dependence needs to be addressed from multiple directions simultaneously. No comprehensive head-to-head comparison between these different approaches has been published yet, and it is entirely possible that the eventual solution to global timing and navigation resilience will not be any single technology, but a layered combination of several of them working together, each covering the weaknesses of the others. It is a bit like the way modern cybersecurity rarely relies on a single defense. Nobody protects a network with just a password, or just a firewall, or just an intrusion detection system. Real resilience comes from layering multiple independent defenses so that a failure in one does not compromise the whole. Positioning, navigation, and timing. Security appears to be heading in the same direction, where quantum entanglement handles tamper detection on existing satellite links. Self-contained atomic sensors provide a fallback that does not depend on any external signal at all. Revived ground-based radio systems offer a low-cost backup rooted in older but reliable technology, and new satellite constellations in low Earth orbit provide additional redundancy simply by being harder to jam or spoof across an entire larger network at once. Nations that manage to field several of these capabilities in parallel will end up with a genuinely resilient timing and navigation infrastructure, one where an adversary cannot simply defeat the whole system by attacking a single point of failure. That is precisely the kind of layered thinking increasingly shaping defense strategy around the world, and it explains why so many different countries are pursuing so many different technical paths simultaneously rather than betting everything on one approach. What makes the CSIRO achievement particularly notable within this broader landscape is the emphasis on practicality and real-world deployment rather than laboratory demonstration alone. Quantum entanglement has been studied and exploited experimentally for decades, and the physics itself is not new. What is new, and what represents the genuine engineering accomplishment here, is building something rugged enough, compact enough, and reliable enough to move out of a climate-controlled laboratory and into an actual operational environment, generating high flux streams of entangled photons consistently, sending one half of each pair through real atmospheric turbulence and weather conditions up to a real satellite, and maintaining that fragile quantum correlation across the distance despite all the practical noise and interference a real-world deployment involves. That is an extraordinarily difficult engineering problem, one that many research groups around the world have attempted and struggled with, because quantum states are notoriously easy to disturb, and turning delicate laboratory physics into dependable field hardware requires solving dozens of practical problems that never show up in a controlled academic paper. There is also a quieter, longer-term significance to this work that goes beyond navigation and timing alone. Every time a research team manages to take a delicate quantum phenomenon out of the laboratory and prove it can survive in the real world over real distances through real atmospheric interference, it pushes the entire field of quantum technology closer to practical maturity. The same underlying techniques used to generate and distribute entangled photons for secure timing are closely related to the techniques being developed for quantum key distribution in secure communications, and even for early building blocks of future quantum networks that could one day link quantum computers together across cities or continents. In that sense, this device is not just a solution to one specific vulnerability in satellite timing. It is a proof point for an entire emerging category of technology, evidence that entanglement-based systems can move from theoretical promise to field-deployable hardware that governments are willing to actually install and rely on. That is a meaningful milestone in its own right, regardless of how quickly the specific timing application scales up. So, where does this leave us? A team of scientists in Adelaide built a device, roughly the size that could sit on a workbench, capable of generating pairs of entangled photons and sending one member of each pair up through the atmosphere to a satellite hundreds of kilometers overhead, while keeping its twin here on Earth. The entanglement between them holds despite the distance, and because of the fundamental rules of quantum mechanics, any attempt to intercept, copy, or tamper with that link inevitably disturbs it in a way that is immediately detectable. That gives defense, and eventually civilian systems, something they have never truly had before. A genuinely spoof-proof way to verify that a timing signal can be trusted, rather than simply hoping that an attacker lacks the resources or sophistication to fake it convincingly. It will not replace GPS overnight, and it will not instantly appear in every phone or vehicle. What it represents instead is a foundational building block, delivered as working hardware rather than a theoretical proposal, toward a future where the invisible signals underpinning global infrastructure, banking, power, transportation, communication, and defense can finally be protected not just by better locks on the door, but by the unbreakable laws of physics themselves. The next time your phone quietly pinpoints your location in a few seconds, or your bank timestamps a transaction to the microsecond, remember that the whole system rests on a signal weaker than you might imagine, one that has been vulnerable for decades. And somewhere in Adelaide, in a lab connected to a rooftop optical ground station, a small glass cube is quietly splitting light into entangled pairs, sending half of it into orbit, and standing guard over the one thing every system on Earth ultimately depends on, knowing with absolute certainty exactly what time it is. Not guessing, not hoping, not trusting blindly in a fragile whisper from space, but knowing, backed by the unbreakable laws of physics themselves, that the signal is real,